Hey everyone, today we'll talk about another theorem in calculus, the Intermediate Value Theorem. Let's get right into it. Here we have the mathematical statement for the Intermediate Value Theorem. It says that if we have a function f of x that is continuous on the closed interval ab, then there exists at least one number c that's between a and b, such that f of c is between f of a and f of b. Let's break that down a bit. For f of x continuous on AB basically tells us that this theorem only applies to functions that are continuous from x equals a to x equals b, and that includes both x equals a and x equals b. There exists at least one number a is less than or equal to c which is less than or equal to b, tells us that it's possible to find at least one x value that we'll call x equals c that is between x equals a and x equals b, and this x value is going to have the property such that f of c is between f of a and f of b. And all that tells us is that the function value of f of x at that special x value of x equals c is between the function value of the two endpoints. In essence, all this theorem is telling us is that if we have a continuous function, then it has to pass through every y value between its starting y value and its ending y value. I want to highlight that it doesn't matter if f of a or f of b is smaller. The theorem holds in either case as long as we pass through all the points between f of a and f of b. Here's an example that's really going to emphasize the idea behind the intermediate value theorem. Let's say we have a guy named Bob who was 2.5 feet tall when he was a 1-year-old. Then, 17 years later, when he was 18, he was 5.75 feet tall. The first thing we have to realize about height is that it's a continuous function. Our heights can't just instantaneously jump from one height to another. You can't go from being 4 feet tall to 5 feet tall in the blink of an eye, for example. It would be pretty weird to see someone grow 1 foot from one moment to another. So if our friend Bob over here starts at 2.5 feet tall when he was a 1-year-old, he had to pass through every single height between 2.5 feet and 5.75 feet before he reached his final height of 5.75 feet. Let's think about what his height might have looked like as he progressed through life. So maybe when he was really young, he got a bunch of growth spurts that made him grow really quickly. But as he got older and older, his height only grew really slowly. So as you can see here, we had to pass through every single possible height between the age of 1 and the age of 18. And that's all the intermediate value theorem tells us. If a function is continuous, then there must be some x value that gives us an f of x value between the starting value and the ending value. In other words, we have to pass through every single y value. Now I want to think about why the function has to be continuous, and I'll show why with a counterexample. Here we have the graph of f of x, and we see that it has a jump discontinuity. We can easily see that the intermediate value theorem doesn't hold here because there is no x value we can possibly choose between x equals a and x equals b that gives us an f of x value here in this range. Therefore, we need to have continuity for the theorem to hold. What you're seeing here is something similar to when people jump to conclusions. When they jump to conclusions, they skip some crucial points of reason, so you know their thought process didn't go through every point that was important to consider. That's how you mathematically prove you shouldn't listen to people who jump to conclusions. Now let's think about why continuity needs to hold on a closed interval instead of an open interval. Here we see a function that's only continuous on an open interval, which doesn't include x equals a nor x equals b. Once again, we can see that the theorem doesn't hold because there is no x value we can possibly choose that gives us, in this case, any value between f of a and f of b in that range right there. Therefore, we need continuity on a closed interval for the intermediate value theorem to hold in the first place. Something else that's very important to mention about the theorem is that the theorem itself only guarantees that the function passes through any y value once. For example, here we have two graphs that both go from y is equal to 3 to y is equal to 7 as x goes from x is equal to 1 to x is equal to 5. They both have the same conclusion from the intermediate value theorem. They're continuous on the closed interval 1 to 5, so they must pass through every y value between 3 and 7 at least once. But that at least once is what's key. We see here on the graph on the left that is just a linear graph that passes through each y value once, whereas the graph on the right passes several y values multiple times. Thus, from just the intermediate value theorem, we can only guarantee any y value is passed through once, even if the function passes through that y value multiple times. Alright, this problem is giving us a table for a function f of x that's continuous on the closed interval 1, 5. And it's asking us for at least how many times f of x is equal to 2 on that closed interval. Well, this question is asking us how many times f of x passes through 2. So I'd say using the intermediate value theorem here would be a good call. Seeing the table, if x goes from 1 to 2, then y goes from negative 2 to 7. That means that to get to 7 from negative 2, a continuous function would have necessarily passed through y equals 2, since 2 is between negative 2 and 7. So that's one time where we can guarantee that f of x passes through 2 by the intermediate value theorem. When x goes from 2 to 3, y goes from 7 to 5. In this case, 2 is not between 7 and 5, so we cannot conclude that f of x passed through 2. It could very much be the case that f of x had a little dip or something that made it cross y equals 2, but just using the intermediate value theorem, we cannot say that for sure. Looking at when x goes from 3 to 4, y goes from 5 to negative 1. Same process as the first one here. 2 is between 5 and negative 1, so a continuous function has to have passed through 2 by the intermediate value theorem. Finally, when x goes from 4 to 5, y goes from negative 1 to 3. Since 2 is between negative 1 and 3, f of x had to have passed through 2 by the intermediate value theorem. In total, we tallied up 3 times that we can guarantee that f of x passes through y is equal to 2, or in other words, that f of x equals 2. So that right there is our final answer. Now we've got this problem asking us to show that f of x equals 2x squared plus x minus 1 has a root between x equals 0 and x equals 1. Well, let's think about what it means for f of x to have a root in the first place. That just means f of x equals 0. Knowing that f of x is continuous since it's a polynomial, if we can show that f of x passes through y equals 0 between x equals 0 and x equals 1 using the intermediate value theorem, then we're finished. So let's do that. If we compute f of 0, well, we're just going to get 2 times 0 squared plus 0 minus 1. And ultimately, that just gives us a negative 1. Now, if we try f of 1, since that's our second x value, well, we get 2 times 1 squared plus 1 minus 1. And that is just 2. Seeing that f of x went from y equals negative 1 to y equals 2, we can conclude by the intermediate value theorem that f of x has a root between x equals 0 and x equals 1, since y equals 0 is between negative 1 and 2. This is actually related to something called Bolzano's theorem, but you don't really have to know that for this course. It's basically an interesting corollary of the intermediate value theorem that says that if a continuous function changes sign on an interval, then the function has at least one root on that interval. That just about wraps everything up. Thank you for watching and have a great day.